Why does the gradient point in direction of steepest ascent? So the gradient is just a vector made up of partial with respect to x and partial with respect to y. So we're comparing two slopes here from different points on maybe a three-dimensional surface or whatever. But let's look at it from an intuitive perspective to start with. So if you had slope of 1 in the x direction and 0 slope in the y direction, well, this vector would go 1 in the x direction and 0 in the y direction. So it's pointing in the direction of the heaviest slope. Same thing here. So if we had this slope in the y direction and 0 slope in the x direction, well, then we're going to end up with a vector going like this. So it's pointing in the direction of steepest ascent. In this case, so if we have only a slope of 2 in the y direction and a slope of 10 in the x direction, well then we go 10x's this way, 2y's this way. That would give us a vector that looks like this. So it's trying as hard as it can to point in the x direction. And if the heavier slope is in the y direction, well then we go 2x's this way, 10y's that way. We'd have a vector looking something like this. And so this thing is trying as hard as it can to point in the y direction toward the heavier slope, the steeper slope. So that's intuition. It's not rigorous, but maybe that helps. But let's make it rigorous now. To do that, we're going to use the directional derivative. And if you're not familiar with the directional derivative, it allows you to take a derivative in any direction, not just x or y. And I have a video on that. I'll include the link in the description. If you're not familiar with the directional derivative, I recommend stopping now and watching it first. The directional derivative is the dot product of the gradient and some unit vector that specifies the direction we want to go in. So u here is the directional vector. And since this is a dot product, then we want to use the definition of the dot product, which I'm not going to drive here. It's all over the internet. But vector A dot over vector B is equal to the magnitude of A times the magnitude of B times cosine of the angle between them. And so basically that's what we're doing here. I'm dotting the gradient with the direction vector, and this is what we have. But remember that this is just equal to 1, so we can ignore it. So that gets us to here. So this is going to be some slope, some derivative that is determined by this. And so we want to think where this would have the greatest value. Well, the gradient is just what it is, so that's not going to change. The thing that would change is the value of cosine of theta. And so let's think where the value would be the maximum, and that is when cosine equals 1. So when the value is the greatest, we can ignore this as well. So that basically brings us down to that the derivative is going to be the greatest. It's going to have the greatest slope determined only by the gradient vector itself. And so the gradient vector would point in that direction, and then its magnitude would actually give you the derivative, the slope value there. But we can see here that the gradient vector alone is going to point to the direction of steepest ascent.